Hello everyone. So today for this topic, we would talk about IDPF line migration support, and IDPF is known as infrastructure data plane function. So this is the overall agenda. So first, we will take a overview about line migration history, current status, and its problem. And later, we will talk about how IDPF supports line migration, and we will expand in below topic like feature discovery, device state support, DMA logging, and other things. So first, let's take a brief look at what is line migration. So this is the definition from Wiki. Moving a running machine, VM, between different physical machines without disconnecting the client. And let's take this picture as an example. So this is a running VM on the left host. And then if you want to line migrate this VM, it's something like we just schedule this VM from this host to the host on the right. And during the whole process, the VM should be running and there should be no VM power off or kind of disconnecting. So this is the overall concept. So the key is the running VM and without disconnecting. And as you know, the line migration is a mandatory feature in hyperscaler, and its typical use cases include host software upgrades, like you may want to upgrade the hypervisor, orchestrator, or some other host software. And also another use case is load balance. You may want to balance the different server load. And also, if you want to do some hardware maintenance, hardware upgrade, you may also want to schedule the VM running on this machine out of and into the other machines. So next is the line migration status. So when we talk about line migration, VDIO is always one of the most popular solutions everyone knows. And let's take the picture. So VDIO is a specification which helps the communication between the VM and host. And normally in the VDIO, there's a front-end driver and back-end driver. So let's take LAN, for example. The front-end driver is typically as like VDIO net PCI, and the backend driver is like the host. And the front-end driver and the backend driver, they have negotiated and will communication, which follows VDIO spec. And the line migration is just schedule the VM on the left, from the left to the right. So VDIO is known as its good compatibility, and also it's known as its very well supported line migration. And as the network bandwidth requirement is dramatically increasing, so which means we are needing a higher and higher network bandwidth and performance. So what I mean some performance limitation. Part of the reason is that there's one more copy from the host ring to the guest ring, and the whole industry is focusing on how to improving the performance. Part of the method is by redesigning the vhost backend. And when we talk about high performance networking, PCI pass-through is an ideal way to get this. Let's take the picture as example. So typically when we are using a PCI pass-through, we're using the single LV feature, which is whenever we have a physical PF NIC and it can create multiplied VF, and we just pass through this VF into the VM. Through this way, the VM can get near native performance, which is why we call PCI pass-through. And in the Linux framework, when we want to implement the PCI pass-through, usually we leverage the VFR framework for pass-through. And when we talk about the pass-through device, the migration is always been a challenge in the past few years, due to some challenge like the device state migration is a challenge. Also, the dirty page caused by devices is also another challenge. And in the recently, I think the community has very well resolved all these challenges and supported the pass-through devices migration. And in the community, which we are calling this VFL migration. So let's see. So before we talk about the VFL migration, let's see the VFL pass-through framework. So normally, when we talk about single IV solution, so we will have a PF driver and bind with PF device. And at the same time, the PF will also create the VF and let the VF pass through into the VM. And in the VFL pass-through framework, so there's a pass-through driver, which we are calling the VFL PCI driver. And if you're familiar with the VFL pass-through, so the generic VFL PCI is the most popular pass-through driver when we are using the VFL pass-through. So the pass-through framework is like we are binding the pass-through device with a VFL PCI driver. And then when we go to the VFL migration, the VFL migration is extending the VFL UAPI and by introducing some more migration-related callback and UAPI. So, and as you can see that in this way, it extends the VFL device UAPI by introducing the saving, load, suspend, resume device state, and also the log, start, stop, and query UAPI. And the next is our vendor-specific VFL PCI driver. So in the typical pass-through, we just bind them with the generic VFL PCI. But when for the migration, we just extend the migration compatibility from the pass-through driver, which means in this way, we need to introduce a vendor-specific VFL PCI driver. And this driver will do the pass-through, but not only pass-through, but also the migration support. So which means in this vendor-specific VFL PCI driver, we also need to register migration callback and the DMA login callback. And in this way, whenever there's a VFL migration UAPI issued from the user space, it will go into the VFL framework and finally going to our VFL PCI driver and going to this registered callback. And also in the VFL migration model, so all these migration-related primitive or requests is assisted by the PF driver, which means whenever there's a request going from QEMU to Linux to the driver, it will go ask for PF or parent PF driver's help to do this. And in this way, the PF driver needs to export related migration helper to finish all this functionality. So this is the overall migration framework. Then let's see how IDPF support this. So IDPF support this is just follow how community framework define for the LAN migration support. So firstly, you can see that there's the IDPF driver which provides the PF device, and then we create a VF, and then we bind this VF with the IDPF VFL PCI driver with the vendor-specific VFL PCI driver. And in this way, whenever there is a request from the QEMU to kernel to the driver, it will finally go to the IDPF PF driver. And for IDPF cases, things in our IPU, we have management complex running as a resource management agent. This means every request for the migration, the PF driver will get it and forward it to the migration agent, which is running on the management complex. And we will extend all this migration functionality on the Ver channel. So let's take a picture at the overall flow. So first, you can see that there are two hosts here. The left is source host, the right is the destination host. And when we talk about the migration, actually is we are migrating from the left side to the right side. So before the migration start, the administrator may launch the VM on the source side and make it running. And the administrator may also launch the VM on the right, but it is waiting for the migration. At some time, when the administrator issue the command like, okay, please migrate the VM to another place, then the hypervisor will start connection and establish migration channel with the hypervisor on the right. And then we're in the migration stage, and whenever there is any migration-related UAPI, which is issued from the QEMU to the kernel. So it will firstly go into the IDPF VFL PCI driver, and then fall back into the PCI drive, IDPF PF driver. And then the PF driver will forward this request to the IPU through the mailbox of what we call Ver channel. And IPU is the real one who implement and finish this function and doing the real hardware operation. So it's like log the DMA, span device, and saving the device state. And then once we save all the state, we will transfer all these states to the destination side. And on the destination side, which is the right side, we need to load the device state, which is received from the left. And all these load states will fall back into the PF driver and finally go into the IPU, which is the real one who do the hardware configuration and setup. So that is the overall flow. Next, let's see the feature discovery. So there's one background we need to say that why do we need to discover? Because IDPF may be running on different use cases, and not all of the use cases needs migration support. So for example, if we are running IDPF on a host PF NIC and this NIC supports single LV, then we say these cases we may support. But for example, if we are running IDPF on a host PF NIC without single LV support, in this case, we will definitely not support. And also, if we are running IDPF on the guest VF NIC, then also we don't need migration support because migration support is only on the host side. And also, if we have the guest VF has enabled some feature which cannot migrate, then we will also say we cannot support migration. So in order to implement these requirements, we define a per PF capability and a per VF capability. So the per PF, let's take the right picture as example. So while the administrator load the PF driver, so it will, while the PF driver is initializing, it will ask IPU about, hey, tell me what is this device migration status? Is it support or not? And this is only one single bit. And then it just return. And then while we binding the VF PCI driver with the VF device, then while the VF PCI driver is initializing, it will query the PF. What is the migration capability you support? Please tell me. So, and then in the IDPF PF driver, it will first check if the per PF migration bit is enabled or not. So if it is 0, which means that PF itself does not support migration, then we just return 0, telling that we are not supporting any migration capabilities. And then if per PF migration bit is 1, then we will continue query what is the per VF migration capabilities. So this per VF migration capability is more per VF features, which means what specific migration features you support. And some migration feature is mandatory and some is optional, and it depends on the specific use cases. So, and after query IPU, what is the per VF migration capabilities? So if the result is that VF has no migration cap support anymore, then we just return 0. Otherwise, we just return the specific capabilities we get. So, and the overall capability may include stop copy, pre-copy, and DMA log. So the stop copy means we can stop device in the copy state at the stop copy stage, and pre-copy, which means we can pre-copy device state before stop, which is in the pre-copy stage. And the DMA logging means we can support log DMA write, and I will explain some more details about what is these things and when should we use this. Okay, so let's see the first two migration capabilities, which is the pre-copy and stop copy. And this is about the device states part. So before this, let's see some pre-copy background on the migration. So when we migrate a VM from the left to the right, we just copy everything from the left to the right. And then on the right, we just restore everything. So that is the very simple idea and very straightforward. But if we directly copy all these things from the left to the right, it may take too much time. For example, if we have a VM with several hundred gigabyte memory, then it may take too much time to copy everything from left to the right. And this may cause some service timeout, which is not acceptable. So in order to eliminate this issue, we could pre-copy part of the content from the left to the right, but still keep the VM is running. So in this way, we can eliminate that issue. But as you know, while the VM is running, the data copied at previous cycle may be changed, which means, for example, if we copy everything from left to the right as the last as at this time, and then next time there's a one write behavior that vCPU writes 1 into this place, which means the left side memory for this part is not the same as right. Then we have to copy that data again to make sure the memory on the left and the right is the same. And this means we need to do several round of copies, and that's why we are calling this at pre-copy stage, which is maybe start from round 1, round 2 until round n. And when we think we have copied enough data and we can schedule the VM from the left to the right, then we just stop everything and do the last copy, which is stop and copy stage. So that is in a typical pre-copy lifecycle what it is. And when we talk about migration capability for the pre-copy and stop copy, it just means we can also copy the device state at the pre-copy stage if we support pre-copy. And if we support stop copy, this means we can support copy the device state and stop and copy stage. So that is what this capability means. And in order to support this migration, we need to support this below pre-motive, which means we need to suspend device, save device state, load device state, and resume device state. So that is the pre-motive. And in order to support this pre-motive, the IDPF extends VirChannel 2.0 with the device state related migration command like VirChannel to suspend resume device, save and load device state. And also there's one more command introduced here, which is query device state. So this is because while we're saving the state, we don't know what is the device state size. So we need to query this like state size before we save everything from the IPU. So next is device state definition. So first, let's see how do we define our device state? So this device state is organized in below. So this is, we have a version, we have a control state, we have vendor specific state. So in our control state, it is all about what controls has defined in our virtual channel 2.0 role. So normally a control may contain like what is this device capability, packet type, and how many vPort it has, and what is its vPort state, and also other interrupt related configuration. And when we talk about this vPort state, each vPort may contain like port on and off or off, how many TSQ, RSQ it support, and what is its detailed queue state. And if we go to our specific TSQ state, it may include ring base, ring length, ring head, tail, interrupt, and register. Everything we need to migrate our VM, we will define it very clearly in this state definition. So through this way, we have explicitly defined what is IDPF device state, and this may help different vendors to support IDPF migration as long as it follows this device state definition. And also you can see that in different states or description, we all have a version. This means this may help us to do the backward compatible. And also you can see that we describe the device state in a hierarchy structure. And this can help us very easily describe the state and also very easily parse the state. And since, as you can see, that all this is defined in a version and hierarchy structure, and this can help us extend the device state whenever we will add in the future. So it's very flexible and easy for the future state extension. So next is about the DMA logging capability. And in the device state part, we had some introduction about pre-copy background. So, and whenever we want to migrate a VM, we just copy everything from left to the right, but direct copy may consume too much time. So we just pre-copy part of the memory or other part of the content from left to the right. So, but at the pre-copy stage, when the VM is running, so data may be changed by the vCPU, like, okay, CPU may write something into the memory, and that may cause the memory is not synced to the destination. But also, the memory may also be changed by the device DMA write. And for the CPU changed memory, because hypervisor is managing the vCPU state, so it knows what memory is changed, which is the location. But for the device side, things you can see that the IPU is writing the memory by bypassing the hypervisor. So the hypervisor has no idea which memory it writes and when it writes. Okay, so that may cause the problem that the memory may not be fully synced from the left to the right. So that in the pre-copy stage, we need to provide some method so that hypervisor knows whatever region is right by the device DMA. And that is what we call the DMA log support in the migration capabilities. This means at the pre-copy stage, we can tell the hypervisor what specific memory region is changed by the device. So, and in order to solve this problem, we need to support this log start, stop, and log query pre-motive And for this primitive, IDPF introduced the DMA log related command in the version 2.0. It's like start DMA log, stop DMA log, and query DMA log. So that is the DMA logging part. And the last part is about the vSwitch state support. So let's see the picture first. In a typical virtualized environment deployment, the traffic in the VM will directly go into the device side. And when the traffic is going into the device, so it depends on how the pipeline is configured, and the pipeline configuration determines how the packet is going. It is going to the other VM, or it is going just outside. So the pipeline configuration is the vSwitch state, what we define here. And more specifically, it may include layer 2 forward table, layer 3, and tunnel rules, flow rules, all these related. And as you know, if we want to migrate a VM completely, the vSwitch state is mandatory. And you can see that in our typical cases, the vSwitch is managed by the vSwitch agent in the management complex. And if we want to migrate this part, we have two options here. So the first is that we can just let migration agent to migrate all these migration function to migrate the vSwitch state, which means while we're doing the migration, we can put this vSwitch state into our vendor specific state and just using the migration channel to transfer it from the source side to the destination side, and then load them into the destination side via switch agent again. And for this case, if your vSwitch state is very simple and you have a simple orchestrator, then it should be simple and straightforward enough. And if your vSwitch rule is very complex and has a lot of things to deal with, and also you have a very powerful orchestrator or SDN control, then you could also choose to let the SDN control to transfer all these vSwitch agents, manage the vSwitch state from the source to the destination side, and migrate them successfully. So in that way, we provide two suggestions if you want to migrate vSwitch state. Yeah, and I think this is the last page. Yeah, so let's take some this day takeaway. So the first is that we talks about some background about live migration, and then we introduce how do we discover the live migration feature in our IDPF, because some use cases we may not support them, and also we introduce about how do we support the device state migration, how do we support the DMA logging, and last we're talking about how do we support this vSwitch state migration. Yeah, I think that is all. Yeah, thank you.
Hello. Yeah, sorry. Noob question. How does this compare to the VDPA, so VirtIO with VDPA stuff? I know it's maybe out of scope for this talk, but there's live migration support there as well. So I'm just curious.
So is Fanny in the room? Fanny, can you help?
Yeah, can you hear me? Can you guys hear me?
Funny, your audio is echoing. Let me try it. Yeah, so in the beginning of the talk, Yahweh did compare the VDPA what IO solution for live migration, and a lot of the learning for IDPF comes from that. The big delta is we are trying to use the standard IDPF PF driver and trying to keep things generic rather than using vendor-specific hooks. One way to do that is the VFIO PCIe driver, the IDPF1. It has no connections directly to the device. It's going back to the PF driver, which is using the standard framework for accessing the device for getting the live migration state transfer and the DMA logging and all that stuff. So so we are hoping to definitely learn from that as well as improve on it so that it is does not go into the angle of requiring vendor specific hooks. We are also, one other part that we are hoping to do is publish all the different state structures as part of the IDPF spec for live migration so that it is not an opaque data structure, and then something that will facilitate two vendor devices that if they support the IDPF spec that they can achieve live migration theoretically as long as they can adhere to the same information exchange.
Yeah, one note. I think it was demonstrated at the KVM forum, this cross-device live migration with VDPA. So I think it should work there as well.
I see. Okay.
But it's not exactly the same thing, I understand. Anyway, thank you for the answers.
Okay. Okay. Nobody else has a question. Anything online? Any questions online? There are no questions online. Okay. So let's thank our speakers.